talk about this. So good morning. We're going to work on 2.2 and hopefully part, if not all of 2.3 today. 2.2 is over graphing, which many of you have probably done or been introduced to and moves pretty quick. There was a question Brandon had on the Unit 1 project, asking if he had to do percentages for every item that he did. So in the directions, it says I wanted percentages of your big categories and of your subcategories. But the other day in class, I mentioned you can just forget about the subcategories. I don't really care about that. I mean, that's good for you to itemize for yourself. But as far as on the pie graph and the comparison bar chart, just do your main categories. Make sure they add up to 100% when you do your percents in both the planned and the actual. Does that help on that one, Brandon?
Yeah, it does. Because I know there was stuff on there that I only did for like an hour or two out of the whole week, and I wasn't sure if I should count that or not.
Is it one of your main categories?
No.
But it should be part of a main category. If it's not a main category,
yeah. Yeah, so like I know one night I watched Netflix for a few hours, and I kind of had that in like my like being lazy category where I had like
yeah.
Okay.
Yep. So then it's going to go towards the hours in your lazy category.
Okay, sweet. Thank you.
Yeah. So just do your main categories. If you had like 4 to 6 main categories, put everything in there. That's what you're going to want to do your percentages on. That's what's going to go in your pie chart. That's going to go in your comparison bar chart to the before, after, the planned and actual.
Okay.
Awesome. Okay, so I will have the 2.2 project up, like I mentioned, this afternoon or tomorrow. I wanted everybody to get their Unit 1 project in. In the 2.2 project, you can always go back and find previous data, and I'll explain that when I'm going to make a video on me kind of going through the project. So I want to get that up today or tomorrow. So if everybody has their 2.2 and 2.3 out, so starting on page 139. We've already kind of looked at some graphs really this semester. So let's go to, I'll share my screen and I'm going to show where you all can start working. So a coordinate effort. And this really has a lot to do with what you just are finishing up on your Unit 1 project, because the quote here says, believe you can and you're halfway there. So coordinating effort means you're planning for your week, you're planning for your day, you're planning for your time, you're planning for your schedule, maybe next semester, right? What classes you're going to take, what you have left to take, or, you know, planning items that you need to do at work. Planning is, it just, when I make a plan for my day or my week, it just kind of takes some like load off my brain, because it's like, okay, I have it on paper. I just have to worry about this current thing that's in front of me. So let's just go down. I'm going to have you all start working. We're going to work on page 139, talking about data. So this here is a time series graph on percentage rates of unemployment from 1993 to 2018. So you can see that usually years is going to go on our horizontal, our bottom part of our graph. We're going to be introduced to graphing down here on the next page. So this is the graph of the data that we see prior. And these are the percentage of people that are unemployed. Now, I'm not sure what year, I think it was in the early 2000s, they switched over how they're qualifying unemployed. So it used to be anybody without a job. Now it's anybody that's not actively looking for a job. And I don't know how they decide that. But because it's based on time, it's called a time series graph. So go ahead and start answering 1, 2, and we're going through 5 on page 142. And then we're doing just questions 1 through 4 on page 143, and then flipping over. It actually goes 1 through 18 technically, but I'm going to do some graphing with you towards the end. So I'll let everybody get started. I'll kind of just share our answers here. I'll let you all work and share answers if you want. We'll give everybody a minute here and we'll see what you want to share about this graph. Anybody want to throw out some ideas of what they see for one or two using the table versus the graph, and what are some trends that you see in unemployment?
For number one, it kind of just goes in waves. Like during the recession, it kind of peaked and then went back down over time, and now it's starting to go back up because of COVID.
Yep, it kind of is going down, and then about that 2008, it really spiked right in here. Yep, kind of going down, and it got really low. Actually, 18, 19, 20, well, right before COVID, it was really, really extremely low. Okay. And then what do y'all think about trying to find those trends in the table versus the graph?
I like the graph more, or the graph, because you can visualize it.
Yeah, it just, you can quickly see the jump right from here to here, and then, you know, the big trend in decline here. Anybody have questions so far? So it says, without the numbers running along the bottom side of the graph and down the left side, we wouldn't be able to understand any of the information the graph provides. Those numbers are called the scale for the graph. So that's important, the scaling. And they're always crucial in drawing a graph. Each of the number lines that we write the scale on is called axis. The plural word is called axes. So this one down here is called the x-axis. And this one over here is called the y-axis. And we're going to do a little by hand today, but for the most part, we're going to use Desmos for graphing. That's why I've been encouraging everybody to get an account, because your Unit 2 project is going to be turned in using Desmos. So everybody needs to have a free account. You can do it without an account, but then you can't save it. So it's a free account. To be honest, I use my same JC email and login, so it's super nice and easy. And I've got stuff saved in there for from the last 2 years. So, okay. So let's have everybody move forward here. If you've not graphed before, you can, you know, read through this purple, but it says it gives information from January to October 2019. The average unemployment between January and October, so just that year of 2019, was about 3.7%. So if we wanted to find that on the graph, we would go over to where we think 2019 is. If it's not an exact value, you'd have to do some estimating along the number line. and then go up to where approximately 3.7 is, and there's that dot. So we are basing our graphing on something that's called right here a rectangular coordinate system. Okay, rectangular coordinate system, meaning it kind of makes this like square shaped plus sign. And so it's broken into four areas. We call them quadrants. So this is quadrant one. We're not going to grade you over this, but it is good to know because people use graphs in all sorts of jobs. Especially if you are, just as a citizen looking at data that they're giving us in the media, right, to make decisions about our life. It actually goes counterclockwise. So this is quadrant 2, this is quadrant 3, and this one down here is quadrant 4. And like I said, the left right one is our X. And that one's super nice because it moves just like a number line. This value right here is 0 on that number line. And so everything over here on the X is positive and everything over here on the Y or on the X is negative. Okay. And then this up and down is our Y axis. And so everything on the above this 0 is positive for the Y and everything that below is negative. So we call, when we are graphing X and Y together, like we did up here, we went over on X to 2019 and up on Y to 3.7. We call that a coordinate. Okay, it says coordinates right here. And these coordinates always go in alphabetical order, X and then Y. So if anybody's ever played Battleships when they were younger, I love that game. It kind of works in the same way, right? So we have to have a system so that when we read it, we are all reading it the same way. So X is our left-right movement. And then Y is our up and down movement, up and down, okay? And so this starting point, we also have to have a starting point because if we don't have a starting point, it's hard to find directions places, right? The same if you were giving directions to go somewhere for a friend, they're like, you said to turn left and then right, but which way am I coming from? So that makes a difference. So our origin, we call it, that's written right here, our origin is a special coordinate right here called 0, 0. And that's always right here. Now, if you flip the page, they go over it a little bit more, but they give us one where our scaling goes from -5 to 5 and then -10 to 10. So I'll let you start there if you're not already there. I'm just going to mute myself till you all have questions. How's everybody doing?
Good.
Steven's good. Brandon, Carter, Kelsey, all good?
I am good.
Also, if you want, you can always use the little symbol thing that you can use. It's not in the chat. Mine looks different here. Where you can give me a thumbs up if you want to do that's fine. So I'm just going to put these on here for the recording for our folks at home. So plotting points. So it says, what are the coordinates of the origin? Well, we talked about that on the other side. That's 0, 0. And if I'm not mistaken, let me look here. That is our lesson check. So right here, that is our lesson check. Just want to make sure everybody gets that. Like to give you a heads up on that. So 4 says, look carefully at the number of each axis. So what distance does each box on the grid represent along the x-axis? So we've got 1, 2, 3, 4, 5 dashes. So, and it works out nicely. So those look like they're each 1. And then what about on the y? We have 1, 2, 3, 4, 5 dashes as well, but it goes up to 10. And so because we have 5 dashes and it goes up to 10, it looks like I should be able to count by 2s. 2, 4, 6, 8, 10. So the y's go by 2. Jeez, my allergies today. 5 says plot each of the following points. So remember that we're going X and then Y, and X is my left and right movement, and Y is my up and down movement. And we do them kind of together. So if we're going 4 and 0, I'm going right 4, and then I'm not going up at all, up or down, and that's A. Then the next one is 0, -8. So I'm not going left and right at all, but I'm going down 8 because it's negative. And remember, I have to count by 2. So 2, 4, 6, -8 should be right there. And that is B. C, they're both negative. So I have to go -3 to the left, 1, 2, 3, and those are singles. And then down 4, and those are by 2. So 2, 4. So C should be right here. And then D, they're both positive, 2 and 7. So I'm going to go right 2, and then 7. Remember, I go by 2. So 7 is going to be between 6 and 8. So 2, 4, 6, 8. So 7 should be in the middle, right about here. Everybody get on those? You can give me a little thumbs up if you want. Just want to make sure everybody's doing okay on that. Okay. Okay, so the next page is we're looking at a thermometer here. What does it look like the thermometer temperature is? Well. Anybody want to throw these out there, 1 through 4?
We don't know because there's no values.
Right, there's no scale. So it's a question mark, right? And number 2 says that. Explain why the thermometer is pretty much useless. No scale. Now, if you work in the medical field, you might know, we can tell that these are warmer, right, than these, because usually red is warm and blue is cold, but that's about it. What about 3? What are the coordinates of the point on this graph?
I mean, you could assume they were going by 1, but since there's no scale, you don't know.
Again, we have no idea, no scale. So we're just talking about the importance of scaling. Down below kind of goes about the important features of a good graph. So I want to make sure that you're, kind of read through those if you've not done a lot of graphing. And if everybody's good with that, we can move on to page 144. This is the big graphing part. And I'm going to kind of show you where you don't have to spend too much time on this, because I'd rather have us jump on Desmos. Everybody want to give me the thumbs up or let me know if they're okay to move to page 144? Brandon, are you okay? Everybody else is okay? Because I was hoping to get through all of 2.2. I'm part of 2.3 today, if not all of it. Okay, good. So it says almost everyone is interested in gas prices. They have a very real effect on household budget. The data in the following table show the average price of a gallon of regular unleaded gas in the US between 2006 and 2016. Okay, wow, look how low gas was in 2016. I mean, it was like in the $1.70s this summer, wasn't it? Or last year? It was pretty low. Anybody remember, did it ever get to the $1.60s?
Yeah, when COVID got really bad, it was like $1.40 or so in Grass Lake
Yeah.
area.
What?
It was
You know what,
amazing
though?
because I was working full time as a delivery driver.
Oh, I probably didn't notice because I wasn't going anywhere. Wow, okay.
It was nice. Yeah, I literally paid half for what I do for gas then, and I worked like 7 days a week driving, so it was so nice.
Yeah, that is a blessing. Okay, so you don't have to do this whole column, but I want you to know how to do an ordered pair. There's some important things here. So usually we do an ordered pair, a coordinated pair. Remember, we said the year is our X, and then this is going to be our gas price, Y. But if we did scaling, like we talked about before, if our scaling here was, these were going by 0 to 5 or whatever, and this was going by 0 to 5, 2006 would be off the charts. Excuse me. So we're going to always base our graph on a base year. So they told us here that our base year is 2006. So then we can kind of rescale it so that this becomes our X. And now we're talking about the years after 2006. So does everybody see that 2006 minus itself is 0. 2007, subtracting my base year of 2006 means I'm 1 year after 2006. So if we jumped all the way down to 2015, we would say 2015 minus 2006 is 9. So that's how we get that. They wanted you to practice writing ordered pairs. I'm going to do a couple because that's, like I said, I'd like us to jump on Desmos. So this ordered pair is 0, 232. I'll jump down here. This is 2, 305. Always keep the raw data. Don't do any rounding. This one is 9, 211 and 2000, oops, comma. This one is 10, $1.97. Now, if we were going to plot these by hand on this graph, which we can do, I'm going to show you what it looks like, and then I'm going to encourage that you all get out your Desmos. So this is, if you do it by hand, this is kind of what it would look like. And it's hard just because these are going by 0.5s, and it's hard to estimate where $1.97 or 3.32 would be. So this is kind of what it would look like. Making sure I have a label down here for the years since 2006, and making sure I have a label over here for gas and dollars. But like I said, I'm encouraging us to go to Desmos. So I am going to share my screen, and I'm going to go to Desmos. And I'm going to enter. So to do a table, you're going to hit this plus sign over here. Actually, why don't you, everybody want to raise their hand if you want a minute to get to Desmos? We can take like a 2-minute break so everybody can get their Desmos out and open for those that are going to do that. Okay, Brandon wants some time to get his open. Anybody else? I'm gonna resume recording. Okay, so let's go ahead and I'm gonna make a table. Like I said, you can do that. There's a plus sign up here. If you hit that, it gives you lots of choices. There's notes with the quote sign. Expression means you want to put in an equation. That's what we usually use. Then there's a table. So in the table, I'm going to put my coordinates that I was going to write out. So 0, 1, 2, and it's nice. Notice Desmos, oh, it has a pattern. So you can just keep hitting enter all the way down to, oops, 10. Then in Y1, I'm going to enter my gas prices. If there's anybody that's not using Desmos, if you could double check me here. Oops, I'm not a plus sign. Okay. And you can kind of see it already started plotting points over here. Now, if the scaling wasn't, small, like my graph is already set up to be, I would have to go over here to the left. Does everybody see my table over here to the far left? Does everybody see this little is a magnifying glass? And if I hover over it, it says zoom fit. If I click that, it does the scaling. So it fits to my window and looks natural to read. And you can see here that it looks like down at the bottom, it goes 0, 2, 4, 6, 8. And so my little lines that are faint, it looks like they go by 0.5. So 0.5, 1 in the middle, and then 1.5, and then 2. And then going up and down, it goes by 2, 4, but they're definitely spread out more. And so they're a little bit more rectangular, but again, it looks like it goes by 0.5, 1 in the middle, and then 1.5, and then 2. Any questions over the graph? Give me a thumbs down if there's no questions if you want. So I'm going to pause the recording and I'm going to let you all work on 7 through 13. And then we'll go over that together. And then I thought we could look at 14 and 15 because that's some more data. A little bit different data. Going through 7 through 13 for those at home here. So 7 says, what was the highest price of gas between 2006 and 2016? So questions 7 and 8 are kind of weird because I think that they kind of are the same. Does anybody else think that? Or kind
Yeah,
of
I was
wonder?
confused why it kept asking me that we have 2 separate answers. I was like,
I
huh.
know. So 7 is saying, what was the highest gas price? So you would probably just go and look at the table, right?
Yeah.
Which is what I did. So I'm like 340. Okay, clearly. And then 8 says, when was gas most expensive? Okay, so now I see maybe what they're saying. What was the highest? So here in 7, we gave a dollar amount because it said what, and in 8, they're saying when, but it's essentially the same, right? Because when is the year that goes with what? I just realized that. So it was in 2012. But essentially it's the same because you're going to write year 6 and it was $3.40. So I see now one was what and one was when. So that's the difference. What did everybody get for 9? When did gas prices stay relatively level from one year to the next?
I put 2012 through 2014.
2012 to 2014. Anybody agree with that? Looks like it stayed pretty level. 10 says, over what time spans were gas prices rising? I had a couple. Anybody want to throw one out there?
Yeah, I put 2009 through 2012.
Yep, that was one. I had from 2007 to 2008, it jumped up too, right?
Yeah.
11 says, over what time spans was gas getting cheaper? I had a couple on that one as well.
2015 and 2016.
2015 and 2016.
Yes.
Yep. And I think I even started at 2014. Right? Didn't it start declining in 2014? Well, the first decline was from 2014 to 2015. So yes, I agree, it's somewhere in there. Thanks, Kelsey. And then there was another one because there was the jump from here, right? So this jumped and then this jumped. And so from 2008 to 2009, there was a decline, which was interesting. So I think we might want to pay attention here because 2007 to 2008 was when the economy was kind of like starting to bubble, right? And then it burst 2008 to 2009 and people were losing their jobs and our economy was really bad and gas prices went way low, lower than what they were last summer, right? 2008 to 2009, it was only $1.79. Well, and then gas prices went way up. And so if we think about what happened with COVID, they went down, but actually last summer they were the lowest. And now they're spiking back up again. So hopefully there's not something going on with our economy in the background that we aren't really seeing yet. But has everybody noticed that it's hard to get certain things at the grocery store? I don't know about all by you guys, but I noticed some things over here, certain items. No, nothing for you all. Whew. Okay, 12 says, what was the largest single price change in 1 year? So they're looking for what? So that means dollar amount. What was the largest one?
Was it 2014 to 15? Even though it's decreased.
How much
08
was
to
it?
09.
I found $1.26.
Yeah, 08 to 09.
So 2008 to 9, it went from 305, I think, to 179 was
Yep.
the biggest drop. So it went down $1.
26.
Yeah, I should have actually said 179 minus 305. Okay. 13 says, explain why we didn't bother to include negative values along either axis when drawing the rectangular coordinate system. So why would we not need negative values there?
There aren't negative years and there's not negative gas prices.
Right. So time can't be negative. I mean, so we could go back and look at history right in time, but we would start the graph at 0 then and have a base year. And then also gas prices can't be negative. Although, oops, that's an N, negative. I think it was last summer, not this past summer, but was it the summer before? I think that they were actually basically giving oil away because they couldn't get rid of it. So, so that's an interesting thing when we say gas prices can't be negative. Okay, is everybody ready to move on to 14? So I'm going to let you all take a look at this graph or the data on 14. It says, if I offered you one of the two accounts detailed below, which would you choose and why? And so just give your first initial thought. And I'm going to go to Desmos because I'm going to make a table here. anybody wants to give me their thought on which one they would pick initially, looking at between the two choices.
I'd pick the one on the the one on the left, it goes up by 60 each year, no matter what. And then the other one goes up, it went $50, 52.5, 55.13, and then it just has a steady increase.
Okay, so which one would you pick then?
Probably account 2, because I think I don't know if I'm doing it right in my head, but I think after year 6 it would equal out, and then over time it would keep getting bigger and bigger and bigger.
Okay. The one on the right should look awfully similar to the compound interest that we did the other day.
Mhm.
So, but the simple interest one, we were growing by 50s. This one we're growing by 60s. So I think, anybody else agree with Brandon? I think at some point in the near, like year 7 or 8, that count 2 may just surpass count 1.
Yeah.
So 15 is asking us to fill in what we think is going to happen, make some ordered pairs. We're going to use some skills from unit 2.1, the lesson we did on Tuesday, and then they want us to graph it by hand. We're not doing that. We're going to Desmos. So is everybody ready to learn something new
Yes.
and exciting? So technically in the lesson, we're not introducing this stuff that I'm going to show you. So you're getting a sneak peek for a couple lessons, but I think it's important to like expose students to things a little bit early, because then you can kind of think about it. And then as we go to the lessons, you're like, oh yeah, this is making sense why we're doing it like this. So I'm going to go to, excuse me, Desmos. Can everybody see my Desmos again?
Yeah.
And I've got my time. And my start year was 0. And then my black column right here is going to be my account 1. And I'm going to click and I'm going to make another column, and that's going to be my account 2. So they're side by side. Oh, I keep doing this. I got to name that Y2. You can name it whatever you want. So I'm going to put in this data that we have started for account 2. And if you all want to follow along. And then we can take a break, take a 5-minute break or so, and work on 2, 3.
From a year 3 to 4, year 4 it was at $58. So year 5 should be where it hits 60 or plus.
Which one are you talking about? Year what?
Year 5 right there.
Oh,
It go from 3 to 4. It goes from, well, like 11.57 to 12.15, and it's a $58 and some change increase. So year 5 should be where it hits 60.
should be at 60.
Oh, it should be more than 60 for the increase.
Oh, for on the Y2 on my second
Yeah.
column. Okay, so I'm gonna show you how to come up with that. So let's
All
just take this. No, I'm glad that you're kind of thinking ahead there. That's awesome, Brandon. So what I'm gonna do is I'm gonna just take just the raw stuff that we were given. I'm gonna go to my magnifying glass and click on that, and I can see that it does the scaling for me. And it looks like right now the one on the left is ahead of the one on the right. So is everybody in agreement with just that statement, just with what we know?
Yeah.
Okay. So if we go back to the table, Brandon mentioned something that it looks like we're just increasing by 60 every time. So if that's the case, I'm going to go back to my paper for a moment. Oh my gosh. Okay, I thought I paused the recording. I'm like, oh, all that conversation for nothing. So I'm going to go back up here where I've got more space here. So the one up here where Brandon said it looks like we're increasing by 60 every time. What kind of investment would you say this is? Is this a compound interest or a simple interest?
Simple.
So this one is simple. And we learned how to write simple interest the other day, right? We said our amount is equal to the original I'm just using our everyday people terms, plus the increase times time, right? So I can make an expression in Desmos, because if we know the pattern, we can tell Desmos to do the pattern, then it will do the pattern for us forever. Okay, that's the cool thing, is it's like a recipe. Once you figure out the recipe, you can give it to Desmos. Desmos will complete the recipe for future use. So what do we think? How can we write this amount? How can we do this with our numbers here?
Uh, 1,000 plus 60 times whatever the time is.
Okay, so we are starting, our original amount is 1,000 plus 60 is our increase amount times time. I'm going to call that X. In our Desmos, mine is X1. So just so you know, whenever you're doing this, if you've got multiple tables going, which we probably will in unit 2 and 3, sometimes Desmos then will start the next table and say X2. So just pay attention to that. So I'm going to go to Desmos and I'm going to put in 1,000 plus 60 times X1, because that's what ours is. So up here where it says Y1, I'm going to click on Y1. I'm going to backspace and delete that. And I'm going to just type, don't worry, everything went away. I'm going to type what we just said, 1,000 plus 60. And then I don't have to even do a multiplication symbol. I can just type X1. It knows to multiply. And then everything through 4 should be just as it was. And now it's done some future time points for me as well. So I did the ones that were in the table on page 146. I did 5 years, and I did 10, 15, 20, 25. And you can do 50 if you wanted. And then if everybody wants to verify if they got these same values, if they're working in decimals, make sure everybody's getting the same thing. Steven's good. Brandon, Carter, Kelsey, is everybody doing okay? Okay, so Y2, I'm going to go back to my paper. So let's try to work this out for Y2 as well. I'm going to do this one in pink. So for account 2, we said we're not increasing by the same amount. We're gradually getting a little bit more. And so what type of interest did we think account 2 was?
Compound.
Yeah, compound interest, which is an exponential equation. And so with the compound interest, we said our description was the amount at the end of the year was going to be equal to the original. And it was going to be times, right, multiplied by this increase. Actually, it's 1 plus the increase, right, in percent form. And then we're going to raise that to the time. Okay, so that is written out really horrible. So amount A is going to be the original times 1 plus the percent increase to the time. So can we put numbers to this? And now remember I said this looks awfully like what we did on Monday, or I'm sorry, on Tuesday in class. So what was our percent increase then? So we started with 1,000. Does anybody remember the percent increase that you could actually say 50 divided by 1,000 and see what you come up with? That should give you that percent.
0.05.
Yeah, so 0.05. So 1.05, I'm just going to write as 1 plus 0.05. And then I'm going to raise it to time. And my time for this example is X1. So let's go back to Desmos. And Y2 up here, I'm gonna backspace and I'm gonna put in my expression of 1,000. I'll left parentheses to show multiplication, and then I'm just gonna type 1.05. I'm gonna add it, right parentheses. Remember to do an exponent in Desmos as your shift key plus your 6. And then I'm gonna type X1, because again, I wanted to use these X1 values as my inputs. And notice from year 0 to year 4 should be exactly what we had. Now the rounding, because it didn't do any rounding here, right? We had 12.15 in year 4 and 50 cents, but this wouldn't actually round to 51 cents. Okay, so, but if you look at my graph, it doesn't really show anything beyond when the linear, right, the simple interest was above the compound interest. So I'm going to go back to my my magnifying glass and I'm going to hit it again, and it's going to readjust because I have data out here now. And look what happened. So it was, I think, just about year 10. So we can click on year 10 and it will tell us that's the red. We'd have to zoom in a little bit to see, but it looks like it was somewhere, you're right, Brandon, somewhere between 9 and 10, where the exponential became bigger and really made a jump up above the linear, the simple interest. So what I'd like to do is I am going to go down here in 2. I'm going to extend this just a little bit since we have a minute, and we're definitely ahead of where I wanted to be today. This is great. I'm going to teach you all how to do some modeling in Desmos, okay? And again, we're not going to build on this until lessons 2, 4, 5, 6, 7, all those later, and that's okay. It's okay to try something different just to learn. So I'm going to have you write it on your paper. So I want you to go back to, I'm going to go back and do a new share back to my paper for a minute so you can see. So maybe down at the bottom here where you've got a space, or a blank piece of paper where you can keep it separate. Because remember, on the midterm, you're going to want to have a couple of note sheets, like a note sheet front and back for unit 1 and a note sheet front and back for unit 2, so that you've quickly got formulas, kind of like the actual difference and the percent difference, some of those things, and some of these things from unit 2. So for a linear model in Desmos, we are going to do Y, and then you're going to use this thing called a tilde symbol. It's like an approximation symbol. And then we are going to do 1,000 plus 60. Oh, wait, this has to be Y1. So Y1 tilde 1,000 plus 60 X1. The tilde says, I don't know the exact equation, but I want the computer, I want Desmos to come up with, it's called a linear regression equation, okay? I wanted to come up with a linear model and see how well it fits. And then we might as well write it right here. For the exponential, we would do the same thing. And since we know these are linear and exponential, we can do them. But what we're going to be doing in the later lessons is we're going to kind of use the same data, and I'm going to put in both and see which one is better. Right now, we already know this one is linear over here. We already know that this one over here is exponential. So for the exponential, it's going to be Y1, my tilde symbol, then 1,000 parentheses, 1.05, and X1. Wait. This would be, so delete your numbers. We have to pretend that we don't have our numbers. Okay, so we would actually say M here instead of the 1,000, and then we would say B instead of the 60. And this is if we have raw ordered pairs. Okay, like we did prior. And then the exponential would be A instead of 1,000 and B as our growth factor over here instead of 1.05. And this would be if we had raw ordered pairs. Now, we're going to do this here in just a minute. So let me go back. Am I on the Desmos? No, I'm not. Okay. So on the Desmos, because I've already told it an equation here, I think I can go up here and, oh, no, I don't want to do that. Okay, so it's already putting them on there.
I have a question real quick.
Uh-huh.
How did you raise it to like the second, like for the 1000,
Your shift
1.5?
key, your shift key, and at the same time press your 6. You see above your 6 is an upside down V.
Okay, yeah.
Yep. That's called a caret. We call that a caret symbol. And that will do it. Did that help?
Yep.
Awesome. Yay. Yay. Super exciting. Okay. So we're going to leave that. Now, just 1 minute here. I'm going to go down to 2 and I'm going to enter in data. So I'm going to enter this data that I have. I'm going to put in 10 and 15. Okay. And then I'm going to enter in, I'm going to manually enter this data. I'm not going to use an equation like I did up above. Okay, 4 is 1240, 1300, 1600, and 1900. And then I'm going to call that Y3. Okay, so then I'm going to do 1,000, 15. Okay. Oh, geez, bear with me here. And 15 is 2078. Okay. So now since I have raw data, I can do the thing that I told you. So it thinks it has raw data. Because it just says Y2 and Y3 up here, it doesn't know that we've already calculated this. It's pretending that we have raw data. So I'm going to go up here for a minute and turn off those. So if I click on, see where I clicked on here where it was colored, it's going to take those dots off my graph. So it will only have these dots here. Okay. So I'm going to go Y1 and I'm going to use that tilde symbol. And now the tilde symbol is to the left of your 1 key. There should be a key that has that tilde symbol. So you have to hit shift and that symbol. And then I'm going to type M. Whoops, I wrote it wrong when I wrote it for you guys. It was B plus MX. B plus MX, I wrote it opposite. So it's going to be, oops, B plus M, and then I'm using my X2 because my data this time is in X2. And I'm going to hit enter. I didn't like that. Why? Oh, because I used Y1. It's Y2. Remember, I just told you to pay attention to what your Desmos called your data. So I had to use Y2. I want the purple. I want it to come up with an equation to predict my purple using my X2. So does everybody see what happened? Look down here on my printout. It gave me my B is 1,000. That's my starting value. And notice that the way I wrote this up here, Y2 tilde B plus MX2 is what we had. 1,000 is my B, my starting value, and 60 is my repeat amount that I'm adding every time. So everybody see that? And what's cool is it just drew the line here so I can predict in between here. And I want to predict when it actually intersects. like Brandon said. So now I'm gonna go down here and I'm gonna say Y3 and the tilde, and just follow along. You don't have to be typing this. And this is gonna be A times B to the X2. And then whenever we do exponential, we'll get used to this, but we have to click on this log mode box here. So you might want to just take a picture if you can of the screen so you can see how I've typed everything in. And my A is 1,000, just like we said before, it's my starting value, and my multiplier is 1.05. And so now, does everybody see where it drew a solid line for the blue and the green? And I can zoom in and I can find out where they intersect. And it's right there. It put the point of intersection. And Brandon was right. It was between year 8, so 8.2, and the amount was 1492.267. And we're gonna do some of this intersecting, not using equations, not using algebra. That's the cool thing, is we're letting Desmos do the work. It's super amazing. Anybody excited? No? Anybody learn something new?
You definitely learned something new. Yeah.
Cool. So, and don't worry, you're not having to do any of this. This is like a couple lessons on the road. This is like next week. But I wanted to throw it out there just so everybody could kind of see what you're going to be exposed to and why we're learning how to graph today. So I'm going to pause the recording. Let's take like a little maybe 5-minute break. And when we come back, if everybody can open up their 2.3 lesson to page 157. The first half of 2.3 is some of similar like unit conversion, unit rate stuff that we've already done. And so it should go fairly quickly and we'll see what we can get done today. So if everybody wants to turn to page 157 at the bottom. Our quote, of course, says the future is something which everyone reaches at the rate of 60 minutes per hour. Whatever he does, whoever he is. So we all have based on the same time, right? So if you want to read down at the bottom, it talks about equivalent rates. And this is important. A rate is a ratio that compares two quantities, which we did a little bit back in unit 1 in one of the lessons. And I'll have you get started on that, and then I'll check in with you here in just a minute. Did everybody get their initial? Trying to figure out how much money you would make in a 5-day work week.
500.
500. And so what did you do to get there?
I just did 100 times 5.
Okay. And so a little bit of a unit conversion, which most of us would just do naturally, but we don't even think about it being a unit conversion because we make $100 per day, and for 5 days, and our days cancel. And yes, indeed, we'd make $500. And so would we consider these two fractions, $100 per day and $500 for 5 days equivalent rates? And I would say yes. And anybody have a reasoning why? What does that mean? Why can we say that they're equivalent?
Because they can be, well, like the 500 one can be lowered into the 100 one. Like if you divide it.
So they reduce to the same unit rate, actually, right? Because they're both per one when we reduce them. Okay. So if we flip to page 158, it says, question 2 demonstrates a useful fact about rates of change. They can be scaled up or scaled down to fit a given situation. Scaling up a fraction is done by writing an equivalent fraction, that is, one that has the same value using larger numbers. Scaling down is writing an equivalent fraction with smaller numbers. These processes are done by either multiplying both the numerator and denominator by the same number or dividing both the numerator and denominator by the same number. So number 3 says, write a fraction equivalent to 60 miles for 4 hours that has a denominator of 2. So if we have 60 over 4 and we want a denominator of 2, what could I do? Could I multiply 4 by something to get to 2, or could I divide 4 by something to get to 2?
I just divided it all by 2.
Okay, so if we divide by 2, then whatever we do to get this 4 to get to 2, we have to do on top, because the key is this fraction here has to be this, it has to equal 1. Oh, Carter must have gotten. Hey Carter, did you get bumped out there for a bit?
Yeah.
Oh darn. We're on 158. I don't know what point we lost you. So for this fraction, we're scaling down, it's called, because we're dividing the top and bottom by the same number. So we're reducing by a factor of 2. So then my numerator becomes 30 over 2. So this would be 30 miles in 2 hours is equivalent to 60 miles in 4 hours. Now it says write a fraction equivalent to 60 miles over 4 hours that has a denominator of 1. A rate of change with 1 in the denominator is known as a unit rate, which we did unit rates back in our unit 1. So 60 miles over 4 hours. And we want this to be 1 hour. So to get it to a unit rate, we can just take the top divided by the bottom, right? Essentially, we're dividing 60 divided by 4 over 4 divided by 4. So did anybody get this unit rate?
15 miles per 1 hour.
15 miles per 1 hour. So once you have a unit rate, you can scale up as much as you want. So that's the benefit of getting to the unit rate. So it says write a fraction equivalent, and this is a new kind of a new scenario. So write a fraction equivalent to $320 over 4 days that has a 10 in the denominator. Hint, first scale down, then up. So I'm going to get mine to a unit rate by dividing the top divided by the bottom. So I get $80 for 1 day. Then it's a lot easier to scale up to 10 days. So I'm gonna let you all keep working. I'm gonna pause the recording. I'm gonna let you all keep working. It's kind of through the same problem, doing some scaling up and scaling down with this. We've got a runner that runs a certain distance. So I think everybody can see my paper, is that right? I'm sure everybody can see my paper. Okay. So it says if one bicyclist is pedaling at a rate of 40 miles in 3 hours and another at a rate of 50 miles in 4 hours, which is faster? So anybody want to share what they did for this one? This is an important one to understand. It's not the lesson check, but it's an important one to understand. Oh, darn it, Kelsey. You're like, we can't understand you.
By 3 hours and got 13.3.
I heard the last little bit. I think you said you divided the 40 by 3 and you got 13.3. I'm gonna have Stephen add on to this just because I think your voice thing is blurry.
Yeah, I just converted them both to their base rate,
Okay, their unit rate.
our unit rate, yeah.
So this is bicyclist number 1, right? And then it's important to keep the units on here so you know what you're comparing. This is miles to hours. And then what did we get for bicyclist number 2?
12.5 over 1.
Okay. So how do we decide which one is faster?
Bicycle one is faster.
Bicycle 1 is faster? Is everybody in agreement with that? We can travel more miles in the same amount of time. Did anybody build theirs up? I had a student yesterday in my class that built hers up to 12 hours, so they both can get to a multiple of 12. And then she said the same thing. In 12 hours, bicyclist 1 covered more miles. So that's how you would tell. Okay, excellent. Then had everybody already moved on to hopefully 7 through, I'd like to really make sure we get to the first half of 2-3 today, through 16. So the next little story here is about most experienced runners get to a point where they can comfortably jog long distances at a consistent pace. So if you're a runner, once you know your pace, you can kind of get a feel for how you're running and you'll know about how much distance you're going to cover. So it says one particular runner runs a lap that is 400 meters track in 2 minutes. You can assume that the runner can maintain a pace of this for a long time. So 7 says for every blank minutes, the runner jogs blank meters. So we're going to fill in what we know. For every 2 minutes, the runner jogs 400 meters. So they started making a table. It says complete the table, continuing the pattern for times and finding the associated distances for this runner. So if for 2 minutes we traveled 400 meters, then for 4 minutes we should have traveled how many meters?
800.
800. Okay. And then it looks like we're going to go by 2s, right? So 2 minutes, 4, 6, 8, 10, and 12. And then how many meters should we have traveled in 6 minutes?
1200.
Okay. And then 1600 and 2000 and 2400. Did everybody get those? Okay. Carter, Kelsey, Brandon, are we doing okay so far?
I am all good.
Okay. Kelsey got the thumbs up. Carter, are you okay? Okay, so we're gonna use this information to build on 9. So 9 says the rate on which the runner's distance changes is constant. When the rate of change is constant, a quantity illustrates what type of growth that we encountered earlier in this unit. So what type of growth is this? It's a constant change.
Linear.
It's a linear growth. Excellent. Write the runner's rate as a fraction using meters in the numerator. So that's the top, right? So 400 meters for 2 minutes. Write this rate as a unit rate in meters per minute. So what do we get for meters per minute?
200 meters per minute.
200 meters for 1 minute. Okay. Convert your rate from question 11 to meters per second using dimensional analysis. So we want to take 200 meters for 1 minute. And we're going to leave it at meters. So it's still going to be 200 meters, right? And we want it now in seconds per 1 second. So what do we have to do to be able to get this minutes to seconds?
You do you multiply it by 1 minute over 60 seconds.
1 minute over 60 seconds. So my minutes cancel. Okay. So this is going to end up being, in the meantime, 200 over 60. And so this 200 over 60 reduces to what? Because they wanted it per 1 second.
3.34 meters per second. I rounded because it was a repeating.
Okay, 3.34 or I think it's 3.33, right?
Okay.
3.33. It's either way, it's not a big deal. 3.33 meters per 1 second. So it says, what distance will the runner cover in 40 minutes? So we got to make sure we're going back to minutes. So we're going to use the unit rate of minutes to build up to 40 minutes. So 200 meters in 1 minute. And it says what distance? So we just want meters, so we can multiply by the 40 minutes. So my minutes cancel and I get 8,000 meters. Use me on that. Then it says, what distance will he cover in 40 seconds? So I'm going to use my unit rate of seconds. So 3.3 meters for 1 second. To do the same thing, I'm going to multiply by 40 seconds to go back to just my meters unit. So 40 seconds, 3.33 times 40. What did everybody get? 133.2
Yeah.
meters. Okay. So 15 says, based on the previous 2 questions, can you write a formula for finding the distance traveled by an object when you know the speed and amount of time traveling at that speed? So did anybody come up with something? We're trying to find a formula for distance when you know the speed and amount of time. So our speed is really these rates that we have, right? These rates. What did we do with the rates to find out the distance? Because these are the distances right here.
You multiply speed times time.
Yep, speed, and let's call it a rate. So a rate times the time. So this is a formula that you might have used in other classes in high school. Distance equals rate times time. And that's going to be a unit rate is what we're looking for. So D equals rate times time. Okay, so the last question, and then I'll be open for business if anybody has questions over the project or, unit 1 review. And then we'll finish up. We'll go over that in just a minute. So let's do 16. It said, what would this runner's total time be for a 10K race? 10 kilometers, that is. Recall that 1 kilometer is 1,000 meters. So I'm gonna let you, I'll play with that for a minute unless everybody already has it done.
Mine was a little complicated, but basically I did a conversion to how many kilometers it would be per minute, which
Okay.
was 0.2 kilometers per minute.
So can you walk us through how you got there?
Yeah, I did the dimensional analysis of 200 meters over 1 minute times 1 kilometer over 1,000 meters.
Okay, so your meters canceled, so you end up with 200 over 1,000
Yeah,
kilometers per minute. Okay, so what does that come out to be?
0.2 kilometers per minute.
Okay,
And then I just went through a bunch of different numbers to find when 0.2 would equal 10. So I found out that it was a 50.
okay,
So 0.2 times 50, and then the 1 times 50 to get 10 kilometers over 50 minutes.
okay. That totally works. Um, let's see, there's like that. I love that strategy. Let's also see, we can do the distance equals rate times time. And since we know that the distance we want to travel is the 10 kilometers and the rate is 0.2 kilometers for 1 minute, right? If we think of it like that. And then we don't know the time. That's the question, is we want to know how long it will take. So we can divide both sides by the 0.2. So 10 divided by 0.2 should be the 50. I think. Or do I have this mixed around? Yeah, so 10 divided by 0.2 is the 50. So that's another way to get it to 15 minutes. Is my time. So you can use that formula if you want to, working backwards on that one. But I love Stephen's strategy too, because that's just a regular everyday math, right? We don't have to use a formula to get there. Excellent. So I'm going to mark this. So this is where we're dropping off today. And so on Tuesday, we will finish up. We're going to do page 161. So this problem one, it's a car problem. And what your cost is to go in the taxi. And then that goes through, I think it's 1 through 13. And I think we might actually do the problems through 19. I think we do. And that's on a car value. So we do a taxi cab problem and then a car value problem. So problems 1 through 19 on Tuesday. And then we'll move along to get started on lesson 2.4. And 2.4 is going to build us on a little bit more with linear equations. And don't worry, we're going to do a lot in Desmos to help us see some of this stuff. So it's not going to be just a bunch of algebra. I'm going to make sure everybody's comfortable about that. So next Tuesday should be a little 2-3 and 2-4. So I'm going to go and make sure that your 2-3 lesson check isn't due this Sunday. It should be due next Sunday on the 10th. So I'm going to double check that right now. Any questions for me before we go on the project or unit 1 review?
I'm all set.
Okay. Have a great day.
Thank you. You too.
Okay. Bye.
Have a good one.
You too.
Thank you.
Okay, I have
I'm gonna
some